Dijkstra's algorithm using adjacency matrix. In the last lecture, we discussed in detail about Dijkstra's algorithm, but while we were discussing, we considered that the input is provided as an adjacency list. During our graph lectures, that is during our data structures lecture series, we learned that any graph which is having some vertices and edges can be represented by two methods. One is using an adjacency list and the second one is using adjacency matrix. Now you might be thinking, why are we having a separate lecture when the input data structure change from adjacency list to an adjacency matrix? The reason is, coming to a normal algorithm, generally slight changes in the input data structure may not make much change in the algorithm. But coming to this Dijkstra's algorithm, when the input data structure changes from adjacency list to adjacency matrix, the whole algorithm changes. The time complexity changes, the approach changes. Even though the core of the algorithm, the core logic stays the same, when you think it from the implementation side, there is a complete change. That is, we don't even use the min heap that we used in the last lecture. We don't even use this data structure in this algorithm. So let us see how can we implement Dijkstra's algorithm when input is provided as an adjacency matrix. First of all, what is Dijkstra's algorithm? We already learned in the last lecture, but this is an algorithm for finding single source shortest path. That is, given a graph, once you select a source vertex, you will be able to find the shortest path from this source vertex to all other vertices in a weighted graph. And what is the condition that we have? The condition is that there should be no negative weight edges. So given that there are no negative weight edges, Dijkstra's algorithm will provide you the shortest path from a single source to all other vertices, right? So this is what we are going to do. First of all, let us understand what is adjacency matrix and how are we going to store data in an adjacency matrix. So the matrix would look like this. Let us say you have many edges A, B, C, D and so on. Let us now consider you have four vertices in the graph. A, B, C and D. These are the vertices. How do you represent this graph by an adjacency matrix? In this matrix, whenever there is an edge from, let us say, some particular vertex I to vertex J, what will you do in that particular entry? Gij, that entry will be equal to the weight of that edge. That is, if let us say edge AB in the graph is having a weight 3, you will have 3 entered in the entry AB. Similarly, if there is no edge from a particular vertex to another vertex, let us say from A to C, there is no direct edge. The only edge is from B to C. In this case, you will put AC as infinity. And what about those edges between same vertex? From A to A, there is no particular edge, but the distance is 0. So you will write 0 here. So for all the same vertex to same vertex, you will write 0 distance. For all other vertices, if there exists an edge, then you will write the weight of the edge. And if there is no edge, you will put infinity. So this is how you will have entries in adjacency matrix. Given that this adjacency matrix is your input, how are you going to deal with Dijkstra's algorithm? So what are the steps to be followed in Dijkstra's algorithm? In the last lecture, we learned that initially you should know what is the source vertex. Once you select a source vertex, what is the next step? You should find the nearest unvisited node from the source vertex. So if this is your graph and you have this as the source vertex, what should you do? From this source vertex, you should find whichever is the nearest unvisited vertex. And how do you see the nearest unvisited vertex? It is depending on the weight of the edge. If this edge is having a weight of 5 and this is having weight of 6, then 5 is smaller than 6. So A is the nearest unvisited vertex from source S. So this is how you find the nearest unvisited vertex. Once you find that, what should you do? You should find all the neighbors of the vertex A, and then you should relax all the neighbors. This is what we learned in the last lecture. So the difference here is, in the last lecture you used a min heap, but this time you won't be using a min heap, and I'll explain the reason when we reach there, because then you will easily understand. So once you see all the neighbors, what should you do? You should relax, that is, update the distances to all the neighbors of A. Then you should continue this step in a loop till the point you visit all the vertices. So this is what you are going to do in Dijkstra's algorithm. So this basic overview is same for both the lectures, but we'll see the difference when we look into the implementation now. So your input is an adjacency matrix. What is the next thing? Once you have adjacency matrix as the input, you are going to have a source vertex. Starting with the source vertex, what is the next step? So now we are going to also think about implementation. Okay. In implementation, you should have a distance array. What should be the distance array? In this, you are going to have your final result. So you should have distance to each vertex from the source vertex in this distance array. So distance to source D of S should be equal to 0, and distance to all other nodes should be infinity. So infinity in all other entries and 0 in the distance to source. This is your starting point. What is the other array that you want? In the last lecture, we discussed that you should have one more array called the visited array. Why should you have this? This will tell you whether this particular node is visited or not. So you have to visit all the vertices. Whenever you complete visiting of all vertices, you are done with your Dijkstra's algorithm. One thing is, we had a step here in which you added an entry 0 and source vertex to the min heap. But coming to adjacency matrix representation, you won't be using min heap at all. So this step we are going to skip. So we are directly going to enter into the loop. So now you are going to have iteration. From here, whatever steps I am going to say, you have to iteratively go through these steps again and again. That is, whatever steps we are going to write here, you should keep continuing the same things in a loop till the point all your vertices get visited. So let us say, first step. What is the first step? Pick the nearest unvisited node. How do you see which is the nearest unvisited node to the source? So nearest in the sense, smallest distance. So how will you see the smallest distance among the unvisited nodes? You have to pick the one with smallest distance. In the previous lecture, this is where we use the heap. So if you remember, finding the smallest one is exactly where we use the heap. This time, if you want to find the smallest one, if you are not using the heap, that means you have to go through all the available vertices. You have to go through each vertex. You have to see what is the present distance to all those, and you have to manually identify which is the smaller distanced vertex from the source. So this will take order of V time, but still we are going to do this step. You'll understand why we are doing this. So let us say you identified node U as the node with smallest distance right now. At the present point, let us say U is having smallest distance. What should you do? You should check whether U is already visited. If it is not visited, that is in this array, you will check whether U is already visited. If it is not visited, then what should you do? You should add U into this visited array. So you will not add, you have to mark the entry corresponding to U as visited. So let us say this is U, you will tick that particular entry. So tick means in implementation, you will do true or false in a Boolean array. Okay. So the next step is to relax all the neighbors of U. All the neighbors of U. So how do you find? Let us call each neighbor as V. What we'll do? We'll relax each neighbor of U. This is where you have to be careful. In case of adjacency list, you had a special luxury that for each vertex, you directly had a list which told you that these are the neighbors. So you could directly identify whichever is a neighboring node of that particular node. It was easier in adjacency list. But here that you are having an adjacency matrix representation, if you want to see the neighboring nodes to any particular node, let us say for node A, you want to see which are the neighboring nodes, the only option is you have to go through all the nodes in this array. If the value is infinity, that means there is no edge from A to that node. If the value is some particular weight, that means there is an edge with weight of that particular value. So you have to go through all the nodes in the adjacency matrix, that is one complete row, which means this single step of finding all the neighbors will take order of v time. And once you find the neighbors, what should you do? Once you find the neighbor, let us say you found list of neighbors called v, you took one particular neighbor from there, what will you do? You'll check whatever is the particular distance to that v. If that distance is smaller, that is, let us say you will find distance of v, this is equal to distance of u plus whatever be the weight. So here it should be a check whether distance of v is greater than distance of u plus w. Is this greater? That is, u is your present node. You know that there is a path through u to v, which is whatever is the distance till u plus the edge uv, because v is a neighbor of u. So if the w is the weight of this edge, then whatever is the distance till u, that plus w will give you the distance to v. Using that, you should calculate distance to v here and compare with whatever is the existing distance in your distance vector to v. If the present distance is smaller, if this is satisfied, what should you do? You should update distance of v as distance of u plus w. This updation you should do. And after this updation, previously in case of adjacency list representation, you had to add this entry into the min heap. So here again, you don't have to add the entry. The reason is, the point is this: every time at this point in the algorithm, you are going to use up order of v time simply for identifying neighbors. And you know that for each of the vertex, you have to run this loop. So for each of the vertex, you are running this loop, and then for identifying neighbors, anyway, you are using order of v time, which means you will run the loop order of v times, and each time you will use order of v time in order to identify the neighbors of that particular vertex, which means this loop will anyway run for order of v square time. Previously, we were using the min heap so that we can decrease the time here. Why were we able to decrease? Because corresponding to each edge, we had to do relaxing operation, which means order of e into corresponding to each edge, relaxing operation took order of log v time. So considering here it was log e, then in the last lecture we saw how log e turned to log v. Okay, so log e time, which means you can complete this whole loop in order of e log e or e log v, both are the same, that we discussed in the last lecture, in case of adjacency list representation. But coming to adjacency matrix representation, given that you anyway have to use order of v time here and order of v time here, it is better to go for order. Anyway, you are using order of v square. So there is no point in saying order of e log e is better, because e can be maximum v square. So what are you doing here? You are going to say that my time complexity is order of v square now. You are not using heap at all. That part is simplified, and your time complexity will be order of v square. What about the space complexity? See, I am not going into the depth of algorithm because we discussed it in detail in the last lecture. So it will be repetitive for the people who have already watched last lecture. Here I am trying to point out those parts which are the differences between the implementation using adjacency list and adjacency matrix. So this is my major aim in this particular lecture. Okay, so I hope you understood why it is order of v square here. If you understood that, then this particular implementation would be clear for you. Okay. Once it is order of v square, then the next question is, what is the space complexity? Space complexity of this algorithm. What is the additional space taken here? Previously, you took distance vector, visited vector, and the min heap in case of adjacency list representation. But coming to this adjacency matrix representation, you don't have this min heap. You only have a distance vector and a visited vector, which means your total space complexity is only dependent on these two arrays, distance array, visited array, and each of those arrays take order of v space, because whatever be the number of vertices, that is the size of your distance array or the visited array. So your space complexity is order of v. So time complexity of your algorithm is order of v square, space complexity is order of v. So coming to how exactly we understood algorithm in the last lecture, we had gone through a graph like this, and then we are told these are the particular values in the nodes. Let us say A, B, C, D, E, and F. And then we actually did a walkthrough through the algorithm. So this time we are not going to do a complete walkthrough, because the only difference is min heap part is not there. Instead of that, you will be directly identifying. So what we'll do a quick walkthrough so that you understand what is going through, but we won't go step by step. Okay. A is here, 1, 2, 2, 4, 1, 1, 3, and 4. This is what we had in the last lecture. Okay. Let me draw it a bit more neatly. Okay. So let this be the graph. And then I'll have A, B, C, D, E, and F. Then I should have 1 as the weight here. There should be one more edge here with weight 2. This is also having weight 2. This should have 4. This should have 4, 1, 1, and 3. See, I'm just using the same weights that we used in the last lecture so that it is relatable for you. What is the first step? You have source vertex, which is A. You should have a distance array. This is your distance array. This should have one entry for each of the vertices C, D, E, and F. Similarly, you will have a visited array. Visited array should also have one entry for each of these vertices. What is the next thing? Let us say you started with the A vertex, which is your source vertex. You will see whichever are the neighboring. So neighboring vertices you identify. Previously you identify from adjacency list. Here in the adjacency matrix, you have to go through one complete row of the matrix, and you have to see whether there is any edge from A to any of the nodes. So here you will find B and C. What will you do? You will pick B, which is the nearest, and then what will you do? You will mark A as visited, and you will see whichever are the neighboring vertices of B. So neighboring to B, you will find D. You found D. Distance array, you have infinities in all of these and 0 in the source. This is how you start. What will you do then? You will see whatever is the distance to B. Initially you found B. So for B, you updated the distance. Let us say the distance is 1 here. You updated this in the first step. After this, you checked whichever are the neighboring nodes of B. Neighboring node of B you found as D. What will you do then? You will see whether the distance to B, that is how will you find it? Where you should find new distance to D as distance to B plus the edge BD. The distance to B is 1, which we already know from distance array, and edge BD we know it is 4. So ideally you get it from the adjacency matrix. Here I just showed it in the graph. Okay, so this will be 5. So you will update distance to D as 5. So one more thing. Okay, you will update this as 5. And what else should you do? Presently you are visiting B. Okay, so B is updated. And what is the next step? Next step is whichever is the next smaller possible. So again, for the smaller one, you are checking and you will find out. How will you find this out? you will see the distances. And one more thing, distance to C should also be updated when you checked for A. Okay, for A you were checking B as well as C. So in the first step, what did you do? You took A as the source vertex, you checked whichever are the neighbors, you found B and C as the neighbors. What did you do with B? You updated distance to B as distance to A, which is 0 plus 1, distance to C as distance to A, which is 0 plus 2. Why is 2? Because edge AC is of weight 2. So you updated 1 and 2. I just missed it, so that is why I repeated. So C is also updated as 2. And then what is the next step? You already visited B as well. Next thing, again you will see through the distance array. So this time going through the distance array and finding the smallest will take order of V time, because there is no point in saving the time that you saved by using a min heap. So the you were able to do in log V time. Here you are taking order of V time. Okay. So next thing is C. With C, what will you do? You will relax the neighboring edges of C. What are the neighboring edges? D and E. So I am not considering already visited edges, that is A. Among D and E, what happens when you are visiting C? Let us mark C as visited. What happens from C? You will see D. If you see the distance to D, till C the distance is 2, plus from C, CD is also 2. So distance to D will become 4. So you will update 4 here. How did it become 4? Because C, you know from distance vector, distance is 2. And then edge CD, you know it is having 2. Okay. So that is how it became 4. Next is for E, what will you do? Distance to E, that will be distance to C plus CE. See, I am not directly updating. Once you find this value, that is distance to C plus CE, 2 plus CE is 4, that is equal to 6. I am not directly updating. I am checking in distance vector what is the existing distance of E. So if existing distance of E is already smaller, then you can keep it. But now if you see, existing distance is infinity and newly found distance is 6. That is why I am updating here. Okay. So I'll update distance to E. And after this, what should I do? I should take next smallest edge, next smallest vertex, that is nearest vertex. Next nearest is D, which is having value 4. So once I pick D, what will I do? I'll mark D as visited. Then I'll see distances to E and F. What will I do then? Distance to E can be updated as distance to D plus DE. So distance to D from this distance vector is 4. So I got 4. DE is 1, which means new distance to E is 5. Existing is 6. 5 is smaller than 6. So I'll update this with 5. What is the next step? From D, I can also go to F, which means distance to F can be updated as distance to D plus DF. What is this? Distance to D is 4 plus DF is 1, which means it will be 5. So this will be updated to 5. Next step is which is among the unvisited, that is only these two, which is smallest? E and F. Both are equally small. So let us say we'll take E. I'll mark E as visited. What will I do then? I'll take E. Corresponding to E, F is closer to, F is the only neighboring one to E. I'm not considering C and D because they are already visited. So distance of F is equal to distance of E plus EF. So what will this be? This is equal to distance of E is already 5 plus EF is 3, which is equal to 8. So my total is 8, but existing distance is 5. So I should not change. I should not do anything. What is remaining to be visited? F is remaining to be visited. So I'll visit F again. There is no change, so I'm not doing that. So once F is completed, your complete Dijkstra's algorithm completes. So what is the time and space complexities here? Time complexity is order of V square. Space complexity is order of V. And what about the previous implementation, which was adjacency list representation? In that case, time complexity was order of E log V, or you can say order of E plus V log V. And then your space complexity was order of E plus V. Just considering time complexity, what should we actually use? Should we use an adjacency matrix representation or should we use adjacency list representation? The answer is you should always prefer an adjacency matrix representation when your graph is dense. What is a dense graph? Dense graph means you have a lot of edges in the graph. If you have a lot of edges, then E will be is equal to order of V square, right? If E is order of V square, then what happens? Your time complexity in case of adjacency list representation, whatever technique we use there, if we use the same min heap kind of implementation, what happens is that will become order of E log V, which will be V square log V. This will be a larger value than the actual time complexity of this adjacency matrix representation. So this is why we didn't use min heap in case of adjacency matrix representation, and because of that we made it in order of V square. So whenever your graph is dense, you should go for adjacency matrix representation. It will give you better time complexity. Whenever your graph is sparse, if it is sparse, what happens? If it is sparse, your edges, the number of edges is comparable to the number of vertices. That is, there will be very less number of edges. In this case, if you use the adjacency list representation, what happens to your time complexity? E plus V log V will become order of V log V. And what about the adjacency matrix implementation that we used? Here it will hold as order of V square. So in case of sparse matrix, adjacency list representation will give you better time complexity. So the final verdict is whenever you have a dense graph, you should go for adjacency matrix representation, and whenever you have a sparse graph, that is a graph having very less edges, you should always go for adjacency list representation. One more thing, that is before we conclude the lecture, I just want to clarify on one more thing. That is, in all the greedy lectures, we discussed about two properties that are to be satisfied for a greedy algorithm. One is greedy choice property and the other one is optimal substructure property. So let us just discuss on whether these two properties are followed, because this is very basic. You need to check these properties for every greedy algorithm. So coming to greedy choice property, what does it say? It says whatever be your locally optimal choice, if you keep choosing the locally optimal choice, which is the greedy choice, it should give you the finally global optimum solution. So in this case, what are you doing in each step? You are choosing whichever is the nearest unvisited node, right? Whichever is the nearest unvisited node, that is what you're choosing, which means you are choosing wherever you can reach fastest from the source. This is a greedy approach. And when you do this, what happens? You are finding the fastest from the source for each of the vertices, which means you will end up with the global optimum solution, which is best possible or the shortest path possible for each of the vertices from source. And what about the optimal substructure? Optimal substructure says you should be able to break the problem into smaller subproblems, and your final optimal solution for the bigger problem should be made of optimal solution from smaller problems. So in order to show this, you can say that, let us say there is some path from S to, let us say T, which is optimal. If this is the optimal path and let us say it is passing through U, that means you already found the optimal path to U, SU, at some point of the algorithm, and later used this distance in order to calculate the path ST, which is passing through U, which means your solution for ST is having, inside it, it is having a substructure. The sub part is having distance to U. So you are using that optimal substructure to reach the final solution. So both the greedy choice property as well as the optimal substructure property are followed here, which means you are good to go with the greedy solution. And that is why we use greedy approach for Dijkstra's algorithm. So we already discussed Dijkstra's algorithm using adjacency list and adjacency matrix representations.